So welcome back, everybody. You have your graded test back, and as you probably already know, because I've posted a few announcements about this already, I'm offering you the chance to do test corrections, okay? So just to recap, here's how that's going to go. If you want to do test corrections, which you don't have to, it's totally optional. So that means, if you like the score you got, you don't have to do any extra work, you just leave it. But if you do want to boost your score and learn something as you do this, here's how the test corrections will go. So any problem that you missed, just work it out again on separate paper. Okay, so just do it on some blank notebook paper like you would for your homework, and then staple that to the back of your graded test. If you turn that in on Wednesday, then I'll regrade your test, and the deal is you can get up to 1/4 of the points that you missed back if you do the corrections. Okay, and of course I'm regrading it, so it's not guaranteed that you'll get all those points back. You have to correct everything, do it properly, but that's the best case scenario, okay? So do that by Wednesday. It's going to be due in lecture at the beginning of class, along with homework number 7, okay? And homework number 8, I haven't passed out the worksheet for that yet. I'll do that on Wednesday, but that's going to be due Wednesday of next week. So as I mentioned, we're going to have a Wednesday due date for homework over the next couple weeks until we get back from spring break, okay? So any questions on any of that stuff? And I did pass back everyone's test who's here, right? Okay, so with that said, let's get back into the lecture. It's been a while since we actually did anything in lecture. Last week we had Monday off, and then Wednesday we had the test. So if you remember, what's the topic of the lecture? Capacitance, exactly. And I'm having a little bit of technical trouble here, so I'm going to go off of the computer here, and hopefully this works. Okay, that looks fine. So the last thing we talked about was energy stored in electric fields. And I just want to do a few more examples of that before we move on to the next topic, which is equivalent capacitance. It's a bit more, when we get to equivalent capacitance, it's a little bit more practical and has applications to electrical circuits. But let's do a few more examples of this. Here's the situation. We have a cylindrical capacitor, which consists of a conducting cylinder of radius A equals 1.25 millimeters. That's the small conductor here. And it's surrounded by a larger conducting shell of 1.5 millimeters in radius. So both cylinders have the same length, which is 12.5 centimeters. So here's the question. When the capacitor holds a charge Q equals 325 microcoulombs, how much energy is stored in the capacitor? So we want to make a translation between this amount of charge and an amount of energy stored. So anyone have any ideas as to how we can tackle this? We came up with some formulas last time.
Could we use C is equal to A epsilon naught over D to find C?
So we can't use that here because this is not a parallel plate capacitor. So there's a different formula for the capacitance of this type of cylindrical capacitor, which we actually worked out in last lecture, okay? And again, this was a while ago, so you might want to flip back to your notes. But we did work out what the capacitance is, okay? So actually, I'm going to show you 2 ways we can tackle this problem. The first way involves an integral, which we've been doing this sort of thing over the last few examples. So here's what I'm going to start with. Here is a formula for the electric field between the conductors. And this is something that was worked out previously. So I'm not going to go through it again. But you can get this result using Gauss's law. Okay, but we did this in the very first lecture on capacitance. So if you recall, E between these two conductors is Q divided by 2 pi epsilon naught L times R. Okay? That's the formula we derived. So let me ask you this. Do you remember this thing called electrical energy density? Hopefully. Yeah, this is given by lowercase u. what's the relevant formula for that? It relates to the E field. So in other words, if we know the E field, we know the electrical energy density, which is the energy per unit volume inside our capacitor. And that's going to help us get the total energy.
Was it 1/2 times epsilon naught times the E field squared?
That's correct. That's our energy density formula. So if this is our E field, which again we worked out before using Gauss's law, this should be the energy density. Just take 1/2 times epsilon naught times the E field squared. So we'll do a direct substitution. 1/2 times epsilon naught times E, which is Q divided by 2 pi epsilon naught L times R. And we square E, right? So just to get a good accounting of what we have here, write this in a more sensible way. We have Q squared on top, right? I have 2 squared on the bottom, but I also have another factor of 2 on the bottom from the 1/2 factor overall. So I have a factor of 8 on the bottom. Okay, I take the pi and I square it, so I have pi squared on the bottom. For epsilon naught, what's my overall factor?
3. Cube.
Nope.
No.
It's, see, I have epsilon naught squared on the bottom, and then epsilon naught on top, so it's just one factor of epsilon naught on the bottom, and then I have L squared, R squared, okay? So that's a formula, once again, for the electrical energy density. That's energy per unit volume. That's the meaning of this thing, okay? So how do I go from energy density to just energy, total amount? What do? We integrate it over the volume, right? So if I have my energy density and I integrate that over the entire volume of this object, which is between A and B basically, right? Then I'll get the total energy. So we're going to get a formula for it and then we'll plug the numbers in as a last step, okay? That's the idea. So here we go. Total energy in the capacitor. So this is going to be given by capital U. So just to distinguish that from lowercase u, capital U is given by the integral of our energy density, which is lowercase u, over the volume, which is dV. Okay? Now our energy density is known. We already have that. dV is a volume element. Okay? Does anyone know what I should do with this dV thing, given that I'm dealing with a cylindrical volume element? What was that? Okay, well, here, let's think about it. If I have a cylindrical element of volume, okay? Think of this in the following way. It's a really thin shell that's cylindrically shaped. It has some tiny little thickness dr, and it has some length L, okay? So how would I think about the volume contained here? Well, I would take this area, right? And then I would multiply by this tiny little thickness. And hopefully you remember how to deal with the area for a cylindrical surface like this. It is 2 pi r times L. And if I multiply that by dr, if I multiply that by that little bit of thickness, I get the volume element. Okay, so that's just how it works in a cylindrical geometry like this. Go ahead.
2 pi r L, is that for surface area or volume?
Yep, but if you take that surface area times the thickness,
Oh,
then you get the volume. That's what I'm saying.
okay. Thank you.
Okay? All right, so here's what we have in the integral all together. Let's put in our energy density, U, lowercase, which is Q squared over 8 pi squared epsilon naught L squared R squared. Okay? And then we have our dV, which is 2 pi R times L times dr. So let's take a quick accounting of what's constant, what isn't. So if we think about it, if I'm trying to integrate over the entire volume, I'm going from the inner radius, which we're calling A, to the outer radius, which we're calling B. So radius R, that's definitely not constant in this case, but pretty much everything else is, right? Q is constant, the pi factors, and the numerical factors, and the L factors, those are all things we can pull out, Okay, so to simplify this, here's what we have overall. We have a Q squared on top, of course. Now, I have 2 pi on the top. I have 8 pi squared on the bottom. Overall, that's just 4 pi. Okay, then I have an epsilon naught factor on the bottom, and then I have an L on top with an L squared on the bottom. That's just L on the bottom overall. And then the rest is my R factors, which I have to leave inside the interval. So I have dr on top, and then I have R divided by R squared, so that's just R on the bottom. We agree? So this goes in a radius from A to B. So remember, what I'm doing here is I'm integrating over the volume of this capacitor in order to find out how much energy is stored. And again, this is symbolic, but we'll plug the numbers in as a last step. So does anyone remember how this integral works out? I do want to kind of just skip right ahead. But how does this work out?
Log R.
Yep, that becomes natural log R, and then you evaluate that between A and B, right?
Yeah.
Which means when you write that in a more compact way, you can write it as same constants out front times natural log B divided by A. Okay, so that's how the integral works out. I think we've seen that one a few times, so hopefully you're okay with just skipping to that. And now let's put the numbers in and see what this works out to. So what we have is the amount of charge, which is 325 microcoulombs in this case. So we have, 325 microcoulombs, that's 10 to the minus 6 coulombs. Q gets squared. That's divided by 4 times pi, and then epsilon naught, just remember, is 8.85, 10 to the minus 12. It's got some weird units, which I'll write down here. It's coulombs squared divided by newtons meters squared. The length, L, of the capacitor is 0.125 meters, because it's 12.5 centimeters. That's how we would convert. And then finally, we take the natural log of B, which is the outer radius, divided by A, which is the inner radius. So that was 1.50 divided by 1.25. Both measured in millimeters, but the units just drop right out. Okay, and if we do this calculation, we get the total energy. So here's what it comes out to. If you follow along in your calculator, you should be getting 1,390 joules. So in other words, if you take a cylindrical capacitor that has this dimensions, these set of dimensions, and you charge it to 325 microcoulombs, that's how much energy will be stored. Okay? So I'll admit this is kind of the long way to do this problem. Let me show you the shorter way. Okay. Remember that for a capacitor, the energy stored, given by U, can be written as Q squared divided by 2 times C. Do you remember this one? And do you also remember that we previously worked out in the last lecture on capacitance that for a cylindrical capacitor, there's a formula for C. And it's not the same as the one for a parallel plate capacitor, because remember, each type of capacitor has its own unique formula for this. But I'm just going to show you what we got back then, okay? We got 2 pi epsilon naught L divided by natural log B over A. Okay, so we did this one already. And if we just put that right into our formula for energy, well, guess what? You're going to get the same answer we have here, okay? You're going to get Q squared divided by 4 pi epsilon naught L natural log B over A. That's what you're going to get for the total energy stored, okay? And we already know what happens when we plug the numbers in, so of course we get the same result, right? But in order to do it this way, of course, we need to know that this is the formula for the capacitance, okay? So, any questions on this? Okay. Let's just go back to the slides. Let's try this one. This is kind of a slightly different sort of thing. So here's what's going on in this problem. We have an electrical circuit here, where there's a battery on this side with a voltage of 10 volts. And then we have two different capacitors, which I'm calling C1 and C2, but they're both identical. They have 1 microfarad of capacitance each. Okay, in this circuit, we have something called a switch, okay, where basically we can put the switch in one position and connect a certain set of elements together in the circuit, and we can put it in another position and connect some different elements of the circuit together. Or we can just leave it open like this so that nothing's connected to anything, okay? That's the idea. You can have it open, you can put it at position A, or you can put it at position B, okay? So what I want you to imagine in this scenario is that starting off, everything is completely uncharged. There's no charge on any of the capacitor plates in this situation, okay? But then, what we do is we take the switch and we throw it to position A. So think about what happens when we do that. We take the switch, we put it in position A. What we've done is we've connected the first capacitor, C1, to the battery. So that means the battery is going to charge this capacitor to start off. But C2 is not connected to anything, so it's not going to be charged at all if we just put the switch in position A. So what we're going to start by doing is finding energy stored initially in this capacitor when we do that. Okay, but then we'll switch the situation up a bit. We'll take the switch and move it from position A over to position B. Now let's think about what's happening there, okay? We have capacitor 1, which is already charged up, and now we're connecting it to capacitor 2, which is uncharged. And we're basically allowing the charge to spread out between the two capacitors. That's effectively what happens when we put the switch in position B, okay? So the question then is, how much energy is stored in each one at the end of that process? Okay, so we have some initial energy stored when we're in position A, and then some final energy stored when we're in position B. We're going to calculate both of these things, okay? Is everyone clear on the process here? Okay. So you have one kind of like this on your homework, so better follow along with this one. Okay, so let's start with the first set of questions, which is about the switch in position A. Okay, so with the switch in position A, we have C1 directly connected to the battery. And so what we can easily do is calculate the charge that's going to be on this capacitor. And the way I'll label this is I'll call this Q1 initial. So it's the charge that's on capacitor 1 initially. What's the formula for this? Just C times V, okay? So it's C1 times the voltage of our battery. Okay, let's do that calculation. C1 is 1 microfarad. So it's 1.00, 10 to the minus 6 farads. Okay, what's the equivalent unit for a farad?
Coulombs per volt.
It's a coulomb per volt. That's going to be very useful here, right? Because the battery voltage is 10 volts. So this gives us a very nice clean number, which is 1.00, 10 to the minus 5 coulombs. Okay, so that's how much charge we have on the first capacitor starting off, okay? But then, if we want to calculate the energy stored in this capacitor, well, we have a formula for that. We just brought it out in the previous problem. Remember, this is going to be Q squared divided by 2C, but just to use my labeling system, I have Q1 initial. That's the amount of charge I'm specifically referring to. And the capacitor is C1. Okay? So now we're just going to plug and chug on that one. So I have Q1 initial, that's 1.00, 10 to the minus 5 coulombs, and I'm going to square that guy. And then I'm going to divide by 2 times C1, which is, again, that's 1 microfarad. That's 1 times 10 to the minus 6 coulombs per volt, or farads. Okay, in the previous lecture, I showed you how these units work out. It's a bit of a grind to work through it, but This is an energy, and it does come out in joules if you analyze the units, okay? So let's put a numerical value to this, okay? If you do this calculation, you'll get 5.00 10 to the minus 6 joules. Do we agree with that? Yeah.
Is the C1 squared or?
No, it's, for energy, it's Q squared divided by 2C. That's the formula. Okay. Anything else? Yeah.
You can also use 1/2 of C squared.
Yeah, I could have used, remember for this, we have some variations on it because you can sub out different variables, but I'm just choosing to use this one for the example. All right, so that's pretty much what we wanted to know. This is the initial energy stored in the first capacitor. And then of course in the second capacitor, there's just no energy stored because there's no charge on it yet, right? So that's the answer to the first question. Okay, now let's think about this. Switch in position B. What's going on with the switch in position B? Well, what's happening is the charge, the battery is disconnected with the switch in position B. Okay, it's not connected to anything anymore. It's now C1 and C2 are connected to one another. Okay? And so what we want to say is the charge that was initially just on capacitor 1 is going to spread out between C1 and C2. Okay, that's the idea here. And let me just show you real quick what this looks like. Let's draw it out. So what we have is capacitor C1 over here, which is now directly connected to capacitor C2, which is over here. So you can see that if I had some, let's say, positive charge on this top plate, right, that now gets to spread out between the top plate of capacitor 1 and the top plate of capacitor 2. Okay, because there's a path for it to flow between these two plates. And similarly with the negative plate, right? Whatever negative charge is over here is now spread out between these two plates, okay? So this is what it looks like. We have some new amount of charge on each capacitor, which I'm going to call, so this is the positive plate up here, Q1 final. This is the negative plate down here, Q1 final. And then over here, we have the positive plate, Q2 final, and then the negative plate, Q2 final like this. So what I'm saying is the charge that was initially just on this capacitor is now shared between the two, okay? All right, so with that said, let's write down some equations so we can solve for these two charges, Q1 final, Q2 final. Now the first thing I'll note is that if I take this to be, I don't know, 0.1, and this to be 0.2, notice that the voltage between those 2 points, or the potential difference between these 2 points, can be found by going across the first capacitor. See, I could go from 0.1 to 0.2 by going across this guy, or I could go the other way and go across the second capacitor, right? But here's the thing. It doesn't matter which path I take. I'm still talking about the same potential difference, right? This potential difference, if you recall, just depends on the 2 points, starting and ending point. So what I can say is because the voltage from 1 to 2 is path independent, doesn't matter which way we go, then I can write down the following equation. I can write V1 final, that's the voltage across capacitor 1, equals V2 final. That's the voltage across capacitor 2. And again, it doesn't matter which path I take, so those are the same voltage. Okay? Now, how do I write the voltage across a capacitor? Just think in terms of V, C, and Q. These are the variables we're dealing with here. Yeah, so V is Q divided by C. So I have Q1 final divided by C1 for this guy right here. And then I have Q2 final divided by C2, right? But here's the thing, C1 is just equal to C2. In this problem, they have the same capacitance. So what does that tell us about the charges? Right? They're also the same. So Q1 final equals Q2 final. All right, here's the next thing we're going to do. See, I don't have enough equations yet to solve this whole thing. I have two unknown charges. I've only written down one equation so far, which says the charges are equal. So I need another equation. This equation comes from the fact that charge is conserved. Okay, this is a really important idea. Whatever charge we started off with just on the plates of capacitor 1, again, is now spread out between these two different capacitors. Okay? So I can turn that into an equation. Here's what that looks like, right? What's my initial charge? Well, it's just Q1 initial. And if you like, I can just say plus 0 to indicate that there's no charge on the second capacitor starting off, okay? But then, in the final state, I have Q1 final plus Q2 final, right? Okay? But here's the thing. These are the same exact amount of charge, right? So I could just as well write this as Q1 final plus Q1 final, right? Or just 2Q1 final. Which means if I'm trying to find Q1 final, it's a half of whatever my initial charge was. Okay, you see that? So, in other words, we have the first capacitor hogging all the charge at first, and then at the end it's evenly spread out between the two, so it gets cut in half, right? So Q1 final is a half times this, which is 1.00, 10 to the minus 5 coulombs. And that's pretty easy to do. That's 5.00, 10 to the minus 6 coulombs. And Q2 final is the same thing. So 5.00, 10 to the minus 6 coulombs. So that's how much charge is on each capacitor at the end. Okay? So the last thing we're going to do is calculate how much energy is stored in each capacitor at the end, okay? So U1 final, that's the final amount of energy stored in capacitor 1. Let's just use Q squared over 2C, but I'm going to use the final amount of charge. So here's what we have. Q squared is 5.00, 10 to the minus 6 coulombs squared, divided by 2 times C, which is, again, this is just 1 microfarad, 1.00, 10 to the minus 6 coulombs per volt. Sorry, that does not get squared. Yeah, sorry, I mistakenly wrote that C gets squared, but I did not mean to do that. So yeah, C is not being squared, just Q. All right, so if we calculate what this comes out to, it comes out to 1.25 times 10 to the minus 5 joules. Sorry, I made one more mistake up here. Let me just point it out. For the initial energy, I meant to say this is the minus 5 power, not the minus 6 power, okay? So just make note of that. Okay. So what about the final energy stored in capacitor number 2? It's the same thing, because it's the same exact value of Q and the same exact value of C. So it's 1.25, 10 to the minus 5 joules. Okay, so here's what I want to point out real quick about this whole situation. What is my total energy stored between the two capacitors in the final state? I'm just adding these two together, right? So what do I get? Just take 1.25 plus 1.25, you get. And compare that again to what we started with. I'll just write it down again. The initial energy stored between the two capacitors initially is actually double this. So what's going on here? Would you expect that if we just take two capacitors and we move some charge from one to the other, that the total energy should stay the same? I think that might be the expectation for most people, but it actually doesn't work that way. It turns out we lost some energy in this process. You see that? Can anyone explain that? Why did we lose some energy in this process?
Is it the motion of the electron?
Yeah, exactly. And what happens when the charges move around?
The kinetic energy?
That creates waste heat, so thermal energy.
Yeah, so in order to move the charge from one capacitor to another, you need some electrical current to be going through those wires that connects everything. And when electrical current runs through those wires, it does create waste heat, and some of that energy just gets lost to the environment. We're going to learn about that in the next chapter, but this is just a preview of that sort of thing happening, okay? That's the reason. Yep?
Can you, oh, never mind. You got rid of the square.
Yeah, sorry about that. It's kind of going on autopilot. There's no square there. Okay. Any other questions?
Yes, because can you explain this fact that at the beginning you have a battery which is charging, that
Yeah.
carrying a lot of charge. And the second step, you have another battery who is discharging and putting on the other one, but the charge has split.
Yeah, but
you don't have the same amount of energy for the beginning and the end. Can you explain like that?
so, but the reason for that is you have to account for where is the energy going, or why is it being lost from the system, and that is from the heat generated when current runs through those wires. That's the explanation.
Yeah. What I want to say, because when you use the formula Q squared divided by C,
Yeah,
or here the two values have the same C.
Yeah.
But initially they don't have the same charge.
right.
Finally, they have that's what the relationship Q squared divided by C.
Yeah, so that's correct what you just said. All right, so let's move on to kind of a different topic, which is capacitors in series and parallel, and something called equivalent capacitance. Okay, so this idea of equivalent capacitance, it's going to come up again in this class once we get to resistors. And the idea here is you can take a complicated circuit that has many different elements, in this case capacitors, connected in some way, and in certain cases you can simplify it down to something much simpler where we just have one capacitor. Okay, so that's oftentimes something you want to do, and I'm going to show you how it works. But first, let's start off with this. What does it mean to connect different devices in series and parallel? Now, this really applies to any type of device you might care about. It could be batteries, it could be resistors, it could be capacitors, or any other sort of thing that you put into a circuit. This just has to do with the way they're connected, okay? You can have a series connection, you can have a parallel connection, and it's important to understand the difference. So let's start with series connections. It's pretty straightforward. When you have devices connected in series, charge is going to flow through them along a single conducting path. So imagine we take 3 light bulbs and we connect them in series. This is what it would look like. Maybe this is the outlet that we connect the bulbs to. A wire runs from that outlet to the first bulb, and then another one connects the 2 bulbs together like this, and then another wire connects these 2 like this, and then back to the outlet. So you see everything is connected along a single path like this. So that's a series connection, and one thing to immediately notice about a series connection is that if you break the connection at any point along that path, you break it everywhere. So in other words, if I have some current running through these bulbs, and I maybe cut this cord right here, all of the light bulbs will go out, okay? Because I've broken the conducting path that all the charge is flowing along. Okay. On the other hand, if I do it in parallel like this, each device is connected along a separate conducting path. That's the idea. So here's an example of a series connection for 3 light bulbs. Okay, so we have this cord comes out of the wall outlet. And then we'll connect to that a cord for the first light bulb, like this, another for the second light bulb, like this, another for the third light bulb, like this, and then we'll connect that up back to the outlet. So the point is, each one of these is connected along a different conducting path. That's parallel connections. And again, one thing to notice about this is that if I were to take one of these light bulbs out of the circuit, or maybe cut the cord right here from one of the light bulbs, it wouldn't affect the others. Okay? Current would still be able to flow through the other light bulbs, even if it couldn't flow through one of them. Okay? Because there's just a different path for current to flow for each one. Yeah?
Is that the difference between the cheap Christmas lights and the more expensive Christmas lights?
Yeah, so, right. This is a really bad way to design Christmas lights right here, because you have a single point of failure, right? If I have like 100 different Christmas lights connected like this, I mean, and one goes out, then they all go out. That's not ideal. Yeah, but you're right. It could be a cheaper way to wire it, but it wouldn't be very effective. That's a good example. Okay, anything else? All right. So now let's talk about equivalent capacitance. So the idea here is, let's just imagine a giant network of capacitors. All kinds of different capacitors in this network. Some of them may be connected in series, others may be connected in parallel, and this can be a very complex network of capacitors, okay? But the point is, we're going to connect that entire capacitor network to a battery with voltage V. So we're imagining connecting this entire network of capacitors to this battery with voltage V, okay? And I also want you to imagine that between all of these different capacitors, they draw a total charge Q from the battery, okay? So imagine the total charge that comes through that battery into the capacitor network is Q, okay? So now let's imagine replacing this crazy network of capacitors with just a single capacitor. Okay, so now it's just a battery connected to one single capacitor. And let's imagine it's drawing the same exact charge from that battery. So it's drawing charge Q just like before. So we'll have remember how this works, we'll have a positive plate plus Q and a negative plate minus Q like this. If that's the case, this has the equivalent capacitance of this network of capacitors because it's functioning the same way. It's drawing the same amount of charge from the battery for the same voltage. So that's why we say it has the equivalent capacitance, okay? And that means the equivalent capacitance is just Q, the total charge drawn from the battery, divided by V, the voltage of that battery, okay? And hopefully you can see just from this picture that this will simplify things if we can use this idea, because we're turning a whole bunch of capacitors into a single one, okay? So let's see how this works. It turns out there are different rules we have to remember, whether the capacitors are in series or in parallel. So it's just a different set of rules for series connections and parallel connections to find the equivalent capacitance. Okay? So let's go through that now. So for the time being, we're just going to think about capacitors which are connected in series. Okay? And then we'll do parallel, and I'll show you how things change a bit. But for the time being, let's think about capacitors in series. Let's try to be as general as possible. So let's just say that we have N capacitors that are connected in series, and all of those are connected to a battery. Okay? So N can be whatever you want. We could have 3 capacitors, it could be 10 capacitors, it could be 100 capacitors. You can pick the value of N. But in general, this is what it looks like. Here's our battery, and then here are the N capacitors connected in series. Remember, what this means is you have a single conducting path that connects all the capacitors. Okay, so I'll number them C1, C2, C3, and then ... There could be a whole lot more in here, but let's just keep going. The last one is Cn. Okay, so the first point that I'm going to prove to you is this. Okay, the charge on all of these capacitors has to be the same. They have to have the exact same amount of charge on their plates. So if we look at capacitor C1, and it has charge plus Q on this plate, charge minus Q on that plate, well, the one it's in series with has to have the exact same set of charges on its plates, and the next one and the next one. So they all have the same charge on them. So the way we say this is Q, which is whatever charge is drawn from our battery, is equal to Q1 equals Q2 equals Q3, and so on. They all have the same charge. The other point we're going to prove is this. We're going to prove that the sum of the voltages equals the battery voltage. Okay? So if I add voltage 1 to voltage 2 to voltage 3 and so on, what I get is the total battery voltage when I do that. And then the last thing we're going to prove is this formula here for the equivalent capacitance. Okay? So we're going to go through each one of these points and prove them separately. Okay? So we're going to kind of flip back and forth between this slide and some scratch work because we want to prove these points and convince ourselves that it's true. Okay. So let's first answer the question, why are the charges equal? So I'm going to draw a little picture where we have the battery, and then this will be our first capacitor plate, and then this will be our second one, and then we'll just kind of say dot, 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 because hopefully you'll see the pattern once we do a few of these. Okay. So let's say that some amount of charge Q flows from the battery and onto this first capacitor. So let's say that this plate acquires a charge of plus Q. Okay? What can I say about this capacitor plate? Let me actually label these. A, B, C, D. So what I'm saying is if plate A acquires a charge of positive Q, what can I say about plate B? Yeah, this will acquire a charge negative Q, because in a capacitor the plates do get oppositely charged. Okay, the next thing I'm going to ask you is what then can we say about plate C?
Positive.
Yeah, and what's the reason for that? Let's check it out. So I'm going to draw a little box right here, which contains plate B and plate C. And what I'm going to call this is an island of charge. Because if you think about it, whatever charge is inside of that box can't change. There's no path for charge to flow into this region or out of this region. You see that? It's just two separated plates with empty space in between. So there's no path for charge to flow in or out of that region. So therefore, the total charge in that region stays the same. And here's the thing, the total charge is 0. Because of course, if we start off with uncharged capacitor plates, and then we connect it to a battery to charge it, we started off with 0 charge. That's the idea. So therefore, if I have minus Q on this plate, what am I going to have on this plate so that the total is 0? Plus Q, right? So that's telling me that this plate is plus Q. Okay, what about plate D? It's going to be minus Q. So you see the pattern, right? There's the same amount of charge on each capacitor when they're connected in series like this, and that's the same as whatever charge is provided by the battery. Does that make sense? So hopefully you see how this works.
If your Q is going the other way, would it be swapped?
Yeah. So just it depends on how you hook up the battery, the positive and negative terminals. But the statement that they all have the same charge remains the same. Okay. So the second point. That's why the charges are equal. Why do the voltages add? Let's think about that. Well, let's go back to the original picture. Okay? I want you to look at these 2 points, A and B. Okay? So there are 2 different paths that I could take to get from point A to point B. One of those paths takes me across the battery like this. And then the other path takes me across all of the capacitors all together. So the idea here is VB minus VA, the potential difference between points A and B. Doesn't matter which path we take, right? So one of those paths is just going to give us the battery voltage. And that's it. There's nothing else in this path. The other path is going to take us across each capacitor individually. So it would be the voltage across 1, plus the voltage across 2, plus the voltage across 3, and so on. So the voltages add together to give you that battery voltage when we're connected in series in this sort of way. Okay? So that's the logic behind it. Let's write an equation down, right? So, oops, wrong thing. So VB minus VA is path independent, which means the battery voltage equals V1 plus V2 plus V3. Just add all the voltages together until you've included all the capacitors. That's the idea. Okay. The last thing we want to do is find a formula for the equivalent capacitance. So remember, the idea here is we have a whole bunch of capacitors connected in series, but if I just had one capacitor hooked up to the battery instead, what would its capacitance have to be so that it functions exactly the same way, so that it takes the same amount of charge off the battery, okay? Well, to answer that question, we already have the equation we need, which is right here, so let's get going on that. So what I want to remind you of is a general formula that C is equal to Q divided by V, which means V, whenever we need to sub that into any one of these places, is going to be Q divided by C, okay, for each capacitor. Okay, so take this equation right here. On the right side, we have, guess what, Q1 over C1, right? Plus Q2 over C2. So these are the voltages across the first 2 capacitors, plus Q3 divided by C3, plus ... until you reach the last one, Qn divided by Cn. Okay, now for the battery voltage, remember how this works. The charge that we draw off the battery is Q, and the equivalent capacitance is CEQ. So that's what we would have if we were just a single capacitor connected to this battery. Okay? So Q1, Q2, Q3, all these different charges, they're the same, aren't they? So, and they're also the same as the charge that we draw from the battery. So in fact, these are not just a bunch of different charges, they're all the same. And I can factor that Q out from all of these different terms. So I'm just going to do that. This is just saying the charges are the same. So once I factor that out, I have 1 over C1 plus 1 over C2 plus 1 over C3 plus ... 1 over Cn. Okay? And at this stage, I can cancel out the Q's. This gives me 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3 plus ... 1 over Cn. So this is a really important result, that when capacitors are connected in series, this is how I get the equivalent capacitance of all of those capacitors in series. Okay? It's not that I add them together, it's that I add their reciprocals. Okay? Add the inverses. That's the rule. Okay, so with that said, let's just summarize everything we learned, okay? Okay, 3 points. First point, capacitors in series, they all have the same charge. Second point, their voltages add together. And then third point, the equivalent capacitance for those series capacitors is given by this formula that we just found. 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3 until you've included all of them. So to put this in a more compact way, we could say it's the sum over 1 over C going from I equals 1 to N. Okay? So let's get a little bit of practice using this formula. Okay, try this out. You have 3 capacitors. Each one has a capacitance C, and they're connected in series. So what is the equivalent capacitance of these 3? Just work it out real quick on paper. Give your answer in terms of C. So is it like 4 times C, half of C? What numerical factor goes in front?
It's not quite.
Yeah, you have to do parts. All right, so what's the answer here, everybody? C over 3. Okay? When we have 3 capacitors in series like this, we say 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3.
Could you move the paper down a little bit?
Oh yeah, sorry about that. But here's the thing, they all have the same value of C, right? So I'll just say this is 1 over C plus 1 over C plus 1 over C, which is 3 over C, correct? So C equivalent is just going to be that to the minus 1 power, because I need to invert it to solve for C equivalent, so that's just C over 3. Okay? So the point here is that when you connect capacitors in series like this, you're actually reducing the capacitance, right? This is less capacitance than if I just had a single capacitor with value C, right? It's a third of that. So I'm getting a smaller amount of capacitance out by making them connected in this sort of way, okay?
Why can't we look at it as like CEQ is equal to C1 plus C2 plus C3?
That's not mathematically the same thing.
No.
No. So yeah, you cannot just flip all the fractions like this. Here's how you have to write it. CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3 to the minus 1 power. That is not the same thing as saying C1 plus C2 plus C3. Those are different statements. Okay? All right. So let's keep going with this. Let's try to get a basic sense of why this works for capacitors in series, okay? So I just want to remind you of something we derived in the very first lecture on capacitance, which is for a parallel plate capacitor, C is equal to A times epsilon naught divided by D, okay? So A represents the area of the capacitor plates, and D represents the spacing or the distance between them. So what I want to show you here, and the diagram should make it pretty clear, is that when we connect multiple capacitors in series, effectively what we're doing is we're increasing the value of D, okay? So let's imagine we have these two capacitors in series. So the area of the plates is A. Let's say the distance here is D1 between the first two plates and D2 between the second set of plates here. What we're trying to say is, what sort of equivalent capacitance would we get if we combine these into a single entity? And the answer is, you're effectively getting a capacitor with the same area, but just add the distance, D1 and D2, for the distance between the plates, okay? So we increased D, therefore we've decreased C. So we have less capacitance than if we just had a single one of these. So the equivalent capacitance CEQ is less than any of the individual ones, okay? That's what happens when you connect in series, okay? Any questions on that? So what we're going to do next, of course, is see what happens when you connect them in parallel. It's a different sort of situation. So let's take a look. What we want to do here is imagine that we have N capacitors connected in parallel to a battery, okay? So here's what that looks like. We have the battery over here. This is our first capacitor. This is our second one. This is our third one. And all of these are connected in parallel because each one of them has its own unique connection to the battery, okay? And we can take this as far as you want. You could have 2 of these, you could have 10 of these, you could have 1,000,000 of these. Let's just say the last one in our set is N, okay? So there's some points here that I want you to take away and hopefully be convinced of about voltages, charges, and equivalent capacitance. So we're going to learn some rules about how the voltages work, how the charges work, and how we can write this as a single equivalent capacitance. So let's start with the voltages, okay? This is pretty straightforward. So I want you to take a look at our diagram, and here's point A, and here's point B. And just like before, I want you to imagine going along some path that takes you from point A to point B. Now, do you see that in this circuit, there's a lot of different ways you could get from point A to point B? So one of those ways is to go across the battery. Another of those ways is to go across the first capacitor. We could also go across the second capacitor. You can take any number of paths to get there. But the point is, the voltage is path independent, right? So any path you take, you get the same voltage. So that tells us that the battery voltage is equal to the voltage of capacitor number 1, is equal to the voltage of capacitor number 2, and they're all the same voltage. Because you can make that argument with any one of these. Okay. The other point I want to make is about charges, okay? So when you connect capacitors in parallel like this, it's no longer true that they all have the same charge. Okay, that's not the case. Instead, the charge is split between all of those capacitors. In other words, the total charge being drawn from the battery is going to each one of these capacitors separately. So the total charge coming off the battery should be the sum of all these charges, okay? Let's just try to see this visually, okay? So let's say the total charge coming off the battery is Q, okay? So that's Q. Where does that go? Well, some of it goes along this path and charges capacitor 1. Some of that goes along this path, charges capacitor 2, and so on, right? It gets split between all of these different capacitors. So what we can say is Q, the total charge from the battery, is Q1 plus Q2 plus Q3, and so on. And again, remember that for capacitors, you have a positive plate and a negative plate. So all of these capacitors up here require a positive charge, the ones that are connected to the positive terminal of the battery. All of these plates down here acquire a negative charge. These are the ones connected to the negative plate of the battery, okay? Or the negative terminal of the battery, I should say. Right, and then finally, there's a different rule for how the equivalent capacitance works, which is This time we just straight add them together, and I'll show you how that works. So let's go through it. So each one of those points individually. First point, why are the voltages equal? Well, the reason for that is the potential difference between points A and B on our diagram is path independent. So one of those paths we can take goes across the battery. That gives us the voltage of our battery. Another path goes across capacitor 1. That gives us V1. We can go across capacitor 2 to give us V2, and so on. That's why all the voltages are equal. Okay. Why do the charges add? That's another question. So for this, just think about it this way, okay? Here, let me go back to the picture real quick. Okay. So one thing I want to emphasize here that I forgot to mention before is that we're dealing with a conductor, right? Whatever's connecting these capacitors together, it's some kind of metallic wire, which will be a conductor. And remember, it's electrons that move when charge flows within a conductor, okay? So technically what's happening is electrons are coming off the negative terminal of the battery and flowing this way. So let's see, some electrons will come off the negative terminal of the battery and end up at this negative plate for capacitor number 1. Some will end up over here at this negative plate for capacitor number 2. And some of those electrons will end up over here at the negative plate of capacitor 3. But here's the thing. Charge is also flowing, these electrons are also flowing in this top region. They're coming off of this plate into the battery so that they can flow through the battery and come back up here. It's a circuit, right? So if negative charge comes off of this plate, it makes the plate positive, right? If this plate loses some electrons, it becomes positive, right? So that's why we end up with these oppositely charged plates like that. But if we track the charge, any charge that's moving this way is going to be split between all of these different plates. And that's why the total charge from the battery is Q1 plus Q2 plus Q3, and so on. It just splits between all your different capacitors. Okay, so hopefully that explains it for you. So the total charge from the battery equals the total charge on all the different capacitor plates. Which gives us the formula Q equals Q1 plus Q2 plus Q3, and so on, out to the last one. Okay, so I'm going to take that as our starting point for the last thing, which is the equivalent capacitance. Now, can someone remind me, for a capacitor, if I wanted to solve for the charge, how could I do that?
It would be equivalent capacity times the voltage.
Yeah, so Q is equal to CV is generally what we'll use, and we'll use it in each one of these slots in this formula, okay? So here, on the right side of the equation, I have C1 V1, right? Plus C2 V2, plus C3 V3, and just keep doing that until you've hit all the capacitors, all the way out to Cn Vn. But the total charge drawn from the battery, which is just what we're calling Q here, is our equivalent capacitance times the battery voltage. Okay? But here's the thing. We just said that all of these voltages are exactly the same, right? The battery voltage, V1, V2, they're all the same, correct? So voltages are all the same. which means we can just divide that out. And what we get as a result is CEQ equals C1 plus C2 plus C3 plus however many you have to add together. If we have n capacitors in parallel, their capacitance values add together, okay? So that's the rule for that. Any questions? Okay, so let's go back to the lecture. So that proves the last point, that we just add the capacitance values together to get the equivalent capacitance for n capacitors in parallel, okay? I'm going to ask you the easiest question in the world right now. 3 capacitors, each with capacitance C, are connected in parallel. If I were to combine these into a single equivalent capacitor, what would its capacitance be? Yeah, so this time we can just straight up add C plus C plus C to give us 3C. Okay, but only when they're in parallel. If they're in series, again, it works differently. Okay, so let's keep going with this. For capacitors in parallel, let me just give you kind of an intuition for why it works out this way, okay? So obviously, if we're just adding the C values together, we're getting a greater amount of capacitance out, right, than if we just had a single capacitor, right? One capacitor has less capacitance than an equivalent number of those connected in parallel, right? Because they add. So why is that? Well, let's go back to this same formula we were working with before. If you have a parallel plate capacitor, C is given by A epsilon naught divided by D. So hopefully what you can see from this diagram is get an intuition for the fact that we're effectively increasing the total area of the plates that the charge gets to reside in this case. So here, let's just say we have 2 capacitors in parallel. The first one has plate area A1, the second one has plate area A2. If we imagine combining these together, effectively, we're getting a larger surface area for the plates that the charge gets to sit on. So for that reason, because C is proportional to A, right, as the area gets bigger, we get more capacitance. Hopefully you'll get a sense that our equivalent capacitance here is going to be bigger than any individual one, because we're effectively increasing the area of the plates. Okay? Okay, so now we're going to do a pretty big example of how to use all of these different rules together for connecting capacitors in series and in parallel. Here we have a network of capacitors. Okay, we have C1, C2, C3, C4, C5. Let's just suppose for simplicity that these capacitance values are all the same, 30 microfarads. And we're connected to this battery, which has a voltage of 10 volts. So we're going to do a bunch of things here. First, we're going to find the equivalent capacitance of all of these 5 capacitors. So in other words, if I were to just connect the battery to a single capacitor, what would its capacitance in microfarads have to be so that it functions the same way as these 5? In other words, it takes the same amount of charge off the battery as these 5. Once we have that, we're going to find the charge on each capacitor. So what's Q1 for this guy, what's Q2, Q3, Q4, Q5. And then the last thing we'll do is find the total energy stored in all 5 capacitors. Go ahead.
Is C1 and C2 like different than C3, C4, C5? So C1 and C2 parallel?
So we're gonna get to that, but actually let's look ahead, right? What are some types of connections you can immediately see?
Series and parallel.
All right, which ones are in series? Let's start with that.
3, 4, 5, right?
3, 4, 5 is one big series combination, right? And actually, now imagine we have already done that. We've combined these 3 into a single capacitor. Now what kind of connection do we have? Parallel, right? That is in parallel with this, C1, C2, and then this combination is all in parallel. So that's what we're going to do. We're going to combine these in series to start. and then we're going to combine everything in parallel as a second step, okay? And each step of the way, we're going to note what we know about the charges and the voltages, and that's going to give us the equations we need to solve for Q1, Q2, Q3, Q4, Q5, okay? So here we go. This is our circuit. Let's label some things on the circuit first. So 3, 4, and 5, that's what I want to start with. Those are the ones that are connected in series, okay? Now, I'm going to use the notation here, and the notation may seem a little bit overly complex, but once you do really complicated problems like this, where you have to solve a circuit for a bunch of different charges, and later on for different currents when we get to that, it's really important to be methodical and label things properly. Okay, so that's why I'm doing this. All right, so we have C3, C4, and C5 in series. We agree that's a series connection. Remember what we just learned. When you have capacitors in series, they all have the same charge, okay? So that means Q3 is the same as Q4 is the same as Q5, and that's the same as what I'm going to call Q3, 4, 5. So when we combine these into a single equivalent capacitor, the charge that's there is going to be Q3, 4, 5, because I'm combining those capacitors, 3, 4, and 5 together. What I'm saying here is all of these charges are equal because of the fact that we have a series connection, okay? So let's label those charges on the plates. So for this guy, we have positive and negative, we have positive and negative for each one of them, okay? And I'm using 3, 4, 5 to denote the charge on the combination. Okay, let's do the equivalent capacitance. Okay, since 3, 4, and 5 are in series, remember the rule for equivalent capacitance is we add the inverses. So 1 over C3, 4, 5 is equal to 1 over C3 plus 1 over C4 plus 1 over C5. So that's my combination, 3, 4, 5. What is that going to work out to? Each one of these individually has a capacitance of 30 microfarads. So what will I get for C3, 4, 5? Well, let's do it. We have 1 over 30 plus 1 over 30 plus 1 over 30 to the minus 1 power if I want to solve for that equivalent capacitance, okay? So what does that give me? So here, 3 over 30, right? To the minus 1, so that's 30 over 3, 10. Okay? 10 microfarads, okay? The equivalent capacitance of all these. And remember, it's less than each individual one. That's how it works when you're in series. Okay, here's what you should do at this point. You should redraw the circuit. We've combined a certain set of capacitors, and we've simplified the circuit a little bit. So once you've done that, redraw the circuit because it will help you keep track of things. As you can see, what we're doing is we're combining capacitors, we're redrawing the circuit, combining some more stuff, redrawing the circuit until we're just down to 1. That's what we do. So in this case, I have the equivalent combination C3, 4, 5 right here, and then I have C1 and C2. And remember, we're calling the charge on these plates Q3, 4, 5, and I have the positive and negative value shown here, okay? So are we all good on this so far? Okay, so let's go back to that equivalent circuit we just drew. Let's label, actually, let me go back. Let's account for the fact that now we have parallel connections, right? C1 is in parallel with C2, is in parallel with this equivalent combination, C3, 4, 5. So what I'm going to do is just write down everything I know because of the fact that we have a parallel connection. So remember, capacitors in parallel all have the same voltage. That means V1 is equal to V2 is equal to V345. All of those voltages are exactly the same. That's one thing we know. What can we say about the charges? How's that work?
Q is equal to Q1 plus Q2 plus Q345.
Yeah, so the voltages are the same, but the charges, they add together, okay? Because whatever's coming off the battery, remember, it has to be split between these three different places. So let's draw those charges. On capacitor 1, we have Q1 minus Q1 for the positive and negative plate. We have Q2, and then we have Q345 for this combination. So remember, the total charge coming from the battery is going to go in these three different places, which gives us the equation Q equals Q1 plus Q2 plus Q345. Okay? That's what we have. And if I were to say something about the equivalent capacitance, by the way, of these three, how would that work? So I would just add them, right? Because they're in parallel. I can add this C value to that C value to that C value to get the equivalent capacitance. That's how it works. And of course, once I've combined all these, now I'm just down to one. So I've basically finished the problem at that point, right? So my equivalent capacitance is just take these three and add them together. C1 plus C2 plus C345. We can do that because they're in parallel with each other. Okay? What do I have for C1? What's the value? 30 microfarads plus 30 plus
10.
Okay, 30 plus 30 plus 10. 70 microfarads. Okay? That's the equivalent capacitance of the entire network. 70 microfarads. So we've done that first part, but we now need to find the charge on each one, okay? So we're going to do a little bit of algebra using the equations we've developed here to calculate the total charge on each one, okay? So in order to do that, it helps to draw our equivalent circuit. This is what I call the equivalent circuit because it's as simplified as it can possibly be. We have our battery connected to CEQ, and the total charge on the plates is plus Q and minus Q like this, okay? Okay, and that CEQ again is 70 microfarads. That's where we're at. So can someone tell me, how would I get the total charge drawn from the battery Q? How would I do that?
Big C, Q over V minus Q.
Yeah, Q is just C times V, if you recall. So here, let's do that. The total charge drawn from the battery, which in this notation we just call that Q, remember? That's the battery voltage times CEQ, okay? And what we have is 70 volts for the battery voltage and 70 microfarads for CEQ, which is 70 times 10 to the minus 6 farads or coulombs per volt, which gives us, if you work this out, 7 times 10 to the minus 4 coulombs. That's the total charge coming from the battery, okay? So what we're going to do is we're going to use that to calculate the charge on each individual capacitor, okay? So the way this is kind of working is, to get to this point, we've simplified things way down. We've taken 5 capacitors, we've turned them into one equivalent capacitor. Now we're going to have to expand back out to get to individual charges. That's the next couple steps here, okay? So you have 7 times 10 to the minus 4 coulombs. You could write that as 700 microcoulombs coming from the battery. Okay, let's use this fact to write down an equation. Remember, V1 equals V2 equals V345. Those were the parallel connections, so they all had the same voltage. Okay, we established that earlier. So how could I write those voltages in terms of the charges?
C over V.
Yeah, so if I want to solve for V, it's Q divided by C. Okay?
To do that, you'll need
So
to
Q divided by C. So for V1, it's Q1 divided by C1. For Q2, for V2, sorry, that's Q2 divided by C2. And then for V345, that's Q345 divided by C345. Okay? So we actually have a few things we can learn from this. First of all, if we solve for Q345 using this equation right here, think about it. Take C345 and throw it over on this side next to this. So we have C345 over C1 times Q1 equals Q345. That's what we have. Okay? So how can I relate Q1 and Q2? How do they relate to each other? They're the same, right? Because C1 and C2 are the same. So we can say Q1 and Q2 are the same. But first, let's take this statement and put it into a more simple expression. Remember, C345, we found earlier that was 10 microfarads, and C1 is 30. So that's 10 over 30, or you could just say a third. So Q345 is a third of Q1. That's what we know from this. Okay, if we take Q2 and solve for that, we get Q2 equals C2 over C1 times Q1. And that's 30 over 30 times Q1 because C2 and C1 are the same. In other words, Q2 is the same as Q1. Okay? So we've written these two unknown charges in terms of Q1. That's going to be useful down the line, okay? All right, what else do we know? Remember, Q, the total charge coming off the battery, is the sum of Q1, Q2, and Q345. Remember this? Okay, so let's put our substitutions into that equation, right? So for Q2, I know that's equivalent to Q1, so I'm subbing that right in there, okay? For Q345, I know that's equivalent to a third of Q1, so I'm subbing that right in there, okay? So how can I write this in a more simplified way? Yep, looks like we have 7/3 Q1, right? So Q is equal to 7/3 Q1. So if we want to solve for Q1, that's going to be Q1 equals 3/7 times Q. And we know exactly what Q is, right? It's right here. So 3/7 of this number is going to give us 300 microcoulombs, right? 3/7 of 700 microcoulombs equals 300 microcoulombs. All right, so that's Q1 right there, just to be clear. Q2, sorry, forgot which order we're going in. Q345, let's do that one. That's a third of Q1, right? So take a third of the number we just found. A third of 300 is 100 microcoulombs, okay? And then lastly, here's everything we found, okay? Let's go through it. We already established what Q1 is. We directly solved for it. But we already found that Q2 is the same value, okay? Which is 300. So Q1 and Q2 are both 300 microcoulombs. And then 3, 4, 5, those are the ones that were in series. So those all had the same charge as we found earlier. And that value of the charge is 100 microcoulombs, okay? So that's what we have right here. So we found all the charges. Any questions on how we did that? Basically, we just used the rules that we learned about for series and parallel connections to generate some equations, okay? So any questions on that? Okay. The last thing we're going to do is calculate some energies, okay? So if I want to know how much energy is stored in each capacitor, what formula could I use for that?
1/2 Q squared over C.
Yeah, so 1/2 Q squared over C could work because I have all the Q values, so that should be pretty straightforward just to plug and chug, right? So let's do that. So, and I want to explain that there are a few ways we could go about doing this, okay? if I want to know the total energy stored in all of these capacitors, there's sort of a long way and a short way to do this, okay? The short way is to use the equivalent capacitance, okay? The long way is to do each one individually and then add them together. But what I'm going to show you is we get the same result either way, okay? So let's do the short way. The short way says the total energy is equal to Q squared divided by 2 times CEQ. What does this mean? Q, remember, is the total charge drawn off the battery, and CEQ is the equivalent capacitance of the entire network. So if I use those specific values, that's going to give me the total energy stored in the entire network. Okay? So let's put in those numbers. We have a half Q squared, that's 700 microcoulombs. 700 times 10 to the minus 6 coulombs on top. Remember, CEQ was 70 microfarads. So that's 70 10 to the minus 6 farads. That's what we're plugging in right here. If you do that, you'll see this comes out to 0.0035 joules. Okay? Okay, the long way to do this is to calculate each individual energy for each capacitor separately and then add them all together. So here's what we get. U1 is a half Q1 squared over C1. And so remember the values we came up with here, a half times 300 microcoulombs, that's 300 times 10 to the minus 6 coulombs squared over C1, that's 30 microcoulombs or microfarads, 30 times 10 to the minus 6 farads. Okay? If you do this, you'll find it comes out to 0.0015 joules. Okay, if we do this for capacitor number 2, remember, same exact amount of charge and same C value. So the numbers we plug into this are the same. We get the same result, 0.0015 joules. For capacitor number 3, take Q3 that we found, plug it in there. So that's 100 microcoulombs on top, 100 times 10 to the minus 6 coulombs squared, divided by 30, 10 to the minus 6 farads, multiplied by a half. Here's what you get. 0.001666, and that's a repeating decimal. If you do this for 4, you get the same value because we have the same charge, same capacitance, so you get the same number. And then the same for 5, okay? So these would be the individual energies for the individual capacitors. But when you sum them all together, you can try this out for yourself, you get the same answer. So if U total is U1 plus U2 plus U3 plus U4 plus U5, add those all together, you get the same number, 0.0035 joules. Okay? So it works out the same way. So you can do it the long way like this or the short way like this. Any questions? Okay, so this is the type of problem you're going to see a lot over the next couple weeks, where I give you some kind of network of capacitors. Okay, we have different C values. They're connected, some are connected in series, some are connected in parallel, and they're all connected to some sort of power source like a battery. And your job is to figure out, okay, how does the charge spread out in that network? What's the charge on each capacitor? So now you know how to do that. Okay? So let's do one more quick example, and then we'll get out of here. So here's the circuit. We have a battery voltage of 4 volts, and then we have 3 different capacitors, 1, 2, and 3, which are all 3 microfarads. So my question for you is, how about we do this? I think this problem is kind of long, so we'll do half of it today, half of it on Wednesday. Let's just do this part. Let's find the equivalent capacitance of all 3 capacitors. I want you guys to work that out, and I want you to combine stuff, redraw the circuit, combine stuff again, redraw the circuit until you just have 1 capacitor. Try doing that, and then next time we meet, we'll do the charge calculations, okay? But for now, just try this out. Try to get the equivalent capacitance. Take a few minutes to work on this, and then we'll go through it together. So think about what the first set of capacitors you want to combine would be. What's the first thing you would combine in this circuit?
1, 2.
Yeah, start by doing 1 and 2, redraw the circuit, then combine the next set. Okay, I see that some of you already have this. That's great. If not, let's just go through it together, and then we'll wrap it up after this. So I'm just going to draw the capacitors because for this part, we just want to find CEQ. And again, we're going to start by combining C1 and C2 in parallel. So if I have parallel capacitors, how do I get the equivalent capacitance of the combination? Yeah, so in this case, we can simply add C1 plus C2. And remember, in this case, each one of these has a capacitance of 3 microfarads. So 3 plus 3, 6. Okay, pretty simple. Let's redraw the circuit. So now I have just a single equivalent capacitor, which I'm calling C12, connected to C3. And what kind of connection am I dealing with here? This is in series, right? So C12 and C3 are in series. Which means if I want to do C123, which is the combination of all of those, that's going to be 1 over C12 plus 1 over C3 to the minus 1 power. This is how we have to compute it. Again, that's not the same as just adding them. So we have 1 over 6 microfarads plus 1 over 3 microfarads, because that's the C3 value. And then we take the whole thing to the minus 1 power. And what does that give us? 2. So this entire combination is equivalent to a single capacitor with a capacitance of 2 microfarads. Okay? That's how this works. And we'll end it here for today. We'll wrap up this lecture on Wednesday. You're not getting 2? 1 over 6 plus 1 over 3 to the 1/2 power. Or sorry, not to the minus 1 power.